Welcome to Image Processing with ArcGIS Pro. 12 YouTube videos summarize image processing lab exercises available in a step-by-step lab manual that accompanies this textbook. Download the lab manuals at the site shown and obtain more textbook information at the second site shown publisher's website. Download the lab manual and data used in the lab exercises if you want to use the step-by-step instructions and process the imagery and DEMs while viewing the YouTube videos. The examples used in the videos and lab manual are discussed and shown in the textbook, improving GIS student understanding of essential remote sensing principles and technology while learning how to process and enhance images and DEMs using ArcGIS Pro. The lab manual, a page is shown in the upper right, and 12 YouTube videos are designed for GIS instructors, students, and users who want to do their own processing, enhancement, and information extraction of satellite and airborne images and DEMs using ArcGIS Pro. You can see the 12 exercises, the tutorials listed here. They cover a broad range of image processing tasks, algorithms, and help you find where these tasks are located on the various menus in ArcGIS Pro. The lab exercises require ArcGIS Spatial Analyst extension. Contact Ellis at ellis-geospatial.com for any questions or comments, and visit the publisher's website for more information and resources on the textbook. Lab 11 covers change detection. We'll look at two examples. The first is Mount Diablo, California, with Landsat images acquired 16 days apart, before and after a fire in 2013. Much of that exercise is courtesy of Mike Quinn, who's faculty member at Diablo Valley College in California. And the second example is urban sprawl using Landsat images acquired 25 years apart. Now the key for this difference computation is that the images have to be really aligned perfectly. If there's offset between the pixels from the two different time intervals, you won't get such a good difference image. Now on the right side you can see the catalog with the files in the Mount Diablo fire folder that you can download from the publisher's website. You can see here we've got 4 Landsats and a DEM. So I've already loaded these on the left side. You can see in the view we've got a streaming map showing Mount Diablo State Park. This is the DEM color coded, so we can look at the symbology. Remember, you do a min-max and pick a color scheme. We've got the hillshade, and we can make this transparent. Click on appearance, say make it 50%. We've got a 6-banded Landsat that's been composite is a color IR, so it's bands 432. This is the 7 September 2013 image, and then 16 days later on 23 September you can see there's a difference on this side of Mount Diablo. And then we've got the near IR, which is sensitive to vegetation. This is what it looked like on the 7th of September, and then this is what it looked like on the 23rd of September. So we'll zoom in, and I'll turn off the near IR, and I'll use the swipe tool, highlight the 23 September image, use the swipe tool to see the difference. See, there had previously been some fires on Mount Diablo. You can see that on the 7 September, but then in 23 September, a pretty big fire. We lived out there at that time. And now if I turn on the near IR, it's even more dramatic because this is very sensitive to vegetation. This is before and after. Before and after. Notice some pixels don't change at all, especially away from the fire zone, but even when you get into the interior part between the 7 and 23, this is very important for the difference image. And the other question we can ask is, are these images well aligned? So we'll go to nearest neighbor on both. Click on the top one. Things line up really well when you zoom out, zoom in, zoom out. It's very impressive. It's from the same sensor, and the features are very well aligned. So we're going to have a pretty good difference image based on the near IR. You just use one grayscale band to do the difference image. So I'll look at the 7th September and I'll use my information tool, and you can see on the left side when I'm in this gray zone, I've got to click on the correct one. So I'm clicked on the 7th September, the before, and I'm down in this zone. It's in 75, 49. So my values are ranging. I have some zeros in this area, so we can examine that in a second. I'll go to the 23 September after, and I have much lower values. Many of these pixels are in the 0 along with the top. So if we take a look and we say, well, where's the sun coming from? Where's the peak on this place? And so if I unclick these and I go back to my DEM, this is the crest of Mount Diablo. And so we've got some strong shadows because when we look at the Landsat, where's the sun coming from? At 10 o'clock in the morning in the northern hemisphere. And so you can see this is a shadowed area, and it's shadowed before and after the fire. Now make the difference image, and you go to the raster functions, and right at the top is compute change. And we'll put the 7 September on top, the 23rd September near IR. Our method will be difference, and we just create the new layer. And it's a 32-bit, so let's zoom out. And you know we have to do symbology and min-max. And we get this warning about, yes, do you want to calculate statistics? Yes, we do want to calculate statistics. And we end up with this very dark color scheme. So I'm going to change to a grayscale. And you can start to see that there's this anomaly, and that's the burn scar. And in the contents, we still have these high values, the default extreme values that ArcGIS Pro can handle. And if we go over here to statistics, we want to change our legend into what is actually there. So our range goes from a positive 209 to a negative minus 242 in this image. We only see most of the change here, so I'm going to zoom in a bit, get my tool that I want. And the other thing I know I want to have is resample to the nearest neighbor, so I get a better feel for what the individual pixels, their value when I do the image information. A positive pixel in the burn scar means the after fire pixel is brighter than the before pixel. A negative means that the after fire pixel is darker than the before. And if I put on my information tool and I look, I can see this area is 0. Pixels that are closer to 0 did not change. If I go over here, you'll see I'm at minus 112, minus 37, minus 65 inside the burn scar. Very low values. So the burn scar is darker in the after fire image. I want to make this more dramatic, so I'm going to go to symbology. Say do % click. It doesn't work. See, my histogram is faded, but if I click on this one, now the histogram works. I can just move these bars a little bit and it'll pop in. So now I'm really seeing this difference of the area here is been subjected to the fire. Now you'll notice in the fire zone, the burn zone, there's these areas with no change. So I go to my information tool, and these are 0 right inside the burn scar. So how can this be? Why would the before and after image have the same value? And so we cover this quite a bit in the lab manual, but you have to look at before and after imagery and see if they're consistent with this bright area. And what is that area? These don't, they're dark in both before and after. So what do they probably represent? And I'll leave that because it's a question in the lab manual. Now we can also query, what's the elevation range of this burn scar? So we go to our information tool, but now we click on the DEM. And so when we roam around, we're getting the elevation, and we can fade, turn off some of these layers. We're fading the burn scar over the DEM. And now you see we can drive our, I'll go back to my Explorer, we can move our cursor around, and here we're going to see I have to highlight the DEM, but the elevation down here, what is it, 209 meters? I come up here, 989, so I can get the range of the burn scar from the DEM because it's in the GIS stack over here in my contents. And of course, if we wanted to make our difference image opaque, zoom to layer, we can export this as a GeoTIFF and put it into another GIS data set. So data, export the raster, give it a name, Lab 11, that's good. And we want to use the renderer, but not force the RGB. And now we've got a permanent image, because when we did the compute change, that's just a temporary image. But now we have this permanent that we can zoom in out and send it anywhere we want. It has coordinates, a GIS ready image that we've created from the difference algorithm. Now we'll move to the second part of Lab 11. We're looking at an urban sprawl change detection between 1986 and 2010. So our catalog is shown on the left side. They've already been loaded in the lab manual. The project APRX is supplied. So you just double click on it and you come up with this view. So what we want to do is just examine the layers. You can see I've got areas of interest, and in the lab manual it asks questions. What happened over the 25-year period in these areas of interest? So here's a 742 enhanced color, and this is what it looked like so it'll look like in 1986, a color IR. It's what we call urban sprawl. And we use red in this difference exercise because vegetation strongly absorbs red light, and it turns out to be a good band, better than the near IR for this particular example of suburbia. So we'll go ahead and create our difference image. So we go to imagery, raster functions again, click on compute change. We'll put the 1986 red into the top one. Raster 2 will be the hist match. So I got the grayscales, the histograms to match between the two, vintage Landsat, and it'll be a difference. We create the layer. So once again, I'll zoom out. We end up with this interesting grayscale, minimum, maximum. We have to calculate statistics. I'm going to change this from this greenish, purplish to a grayscale. And again, we want to have the pixel values in this difference image show up. So I'm having good success. There's in the lab manual shows 3 or 4 ways if this doesn't work. But our values, the dark pixels are -209, the darkest, and the brightest pixels are 211. So if there's not much change, we end up with 0, close to 0. So in this area, you see there's not much change. I go into this area and we end up with -150, -103. So it got much darker here in this number 2. And the same over here, much darker, and parts of this became much darker. And so we're in the exercise, we'll examine what happened in these areas. Now the same thing, I'm going to try to accentuate the grayscale in this by going to percent clip. You see it doesn't hold, and my histogram is faded out, but all I have to do is go over here and hit symbology again. My histogram goes live, and just move these bars a little bit. And now it's apparent to the eye, some areas really got darker. And where they got darker, if there was agricultural land before, and then it got paved over. So we'll zoom in and site 1. And we'll just, once again, we want to go and look at this with our nearest neighbor. Question is, are these well aligned? So we'll go back to the 2 images. Same thing, we'll go to nearest neighbor. Nearest neighbor. Did that catch? And you have to ask yourself, is this as aligned as well as the Mount Diablo? So we can look at the edge of this reservoir. And as you roam around, you say, it looks to me like there's a slight offset. You have to push the C key down when you're in this swipe mode. But so much of the area has changed dramatically. But there's a little bit of a shift, so we can't be as exact with our discussion and evaluation because the pixels aren't aligned as well as they could be. It appears between these images that are 25 years apart. So we'll do a little evaluation. Let's go to site 3. See, the difference image has a really interesting pattern. And so we'll look at it in 1986, the red, there's not much absorption in red. This is these are late summer images, so the grassland is pretty much gone. This is what the grassland looked in like 1986. This is what that area looked like in 2010. So our difference image very effectively captures that landform. What is that landform that was put in where the healthy vegetation is really absorbing the light? It's the red band. The red is absorbing the light, making for a very dark image. If we go over to area 2, we say, well, that's another dark image. What happened here? This is what it looked like in 1986. You can see it was urbanized by 2010. And so it was this dry area. There's not much chlorophyll. The vegetation's really stressed out, so the red light isn't absorbed. But once we get suburbia, we're starting to get absorption of the red light. And I want to click on the difference image, and I'll get those values. We're down to minus 105, minus 121. So it really, a lot more vegetation in this side. And in number 4, we're looking at large agricultural plots. It's got a lot of healthy vegetation in here. The red light is being absorbed, so it's dark in 1986. In 2010, the land use has really changed, and now it's been urbanized, and it's brighter. The vegetation in suburbia wasn't as strong as the irrigated vegetation in the corporate land. So here we are, a lot of water, a lot of irrigation out here in Brentwood. 1986, suburbia comes in, there's more housing, there are still trees, but it's not as heavily vegetated and not as irrigated, and we end up with brighter pixels. So areas that are urbanized aren't necessarily darker. They can be lighter depending on what the land use was before. With that, we'll cease the change detection lab number 11.